Hello everyone and a very warm welcome to this video lecture series in which we are talking about neural networks and deep learning. So until now what we have learned in the previous video lecture is that we have optimized very greatly our code that we have written in the non-vectorized version. Okay, so what we have done is basically we have removed some of the for loops and some of those notations that were creating very much complexity in our code. And what we have done is basically we have tried to implement those kind of functions that were pre-made and given to us in the form of libraries to us. And using those functions we have already seen that how we have tried to optimize our code. Now we have extensively tried to optimize the code, but there were some traces or some spaces where the code was not optimized. Basically, whenever we were having say m number of training example, so we need to explicitly use a for loop for iterating over to all the m training examples, and that was the for loop that hasn't been optimized till the last video lecture. So what we are going to do in this video lecture is that we are going to vectorize the logistic regression for loop also. That is, suppose that if we are having m training examples, then instead of using that for loop, how we can vectorize those steps. Okay, so that we are going to see in this video lecture. Okay, so now let us take these equations. Now here this is the first equation, this is the first equation, this is the second one, and this is the third equation. Okay, so now let us consider the first one. Here an equation, output equation is given to us in the form of parameters w and b, and what it is like, z1 equals to w transpose x1 plus b, and this output z1 would be applied to a sigmoid function, and this would produce the final output that would be stored in a new vector a. Okay, so this is the first training example I'll write here. So this is the first training example. Similarly, if we have n number of training examples, so this is the second training example, this is the third training example. Okay, so here we are taking an example where we have only 3 training example, but in real life whenever you will face the real-time data sets, those will have, suppose, a very large number of training example. Suppose here those data sets have m number of training examples. So what we can do if we have those m number of training example, instead of applying explicit for loops, how can we vectorize those functions? Okay, so we'll see mathematical implementation or theoretical implementation using this video lecture. Okay, so now what we have is we have already studied in the first 2 lectures of this video lecture series that we have taken an example of an image where we were classifying that whether that image was an image of a cat or not. So basically that problem was of a logistic regression, and further what we have done in that example is that we have converted that image in the form of an input vector. So if I have a single training example, my vector input vector would have a dimension of nx cross 1. But suppose that if I have um, m number of training example, then what would be my dimension of the input vector? The dimension of my input vector with m training examples would be nx cross m. So I'll write all the notations and whatever I have said till now. Now I'll represent the input feature vector x by capital X. Okay, I'll write these notations in bold so that these notations are very much clear to you. And what my input feature vector x would be, it will be small x1. These are the data in the input feature vector x1, x2. These are the data for input feature vector x2, x3. This is the data for input feature vector x3, and that goes up to xm because we have total m number of training examples in our data set. Okay, so this is the input feature vector x. Okay, I should write here This is the input feature vector. And one thing has to be clearly satisfied or clearly explained over to here is that this is the small notation or the small x that we have written, and this is the capital X that we have written. Okay, so you need to keep the notations in mind before solving these equations and problems in neural networks. And what has to be understood here is that this input feature vector X is nx cross nx comma m dimension vector, or we could also denote it as r nx cross m. Okay, so this is the notation. And so now, what we have to do is we need to write some implementation in Python or any programming language as how we can implement this equation z1 equals to w transpose x1 plus b. So firstly, what we need to do is we need to write some code for this, and then we will implement this output using this output feature vector a. Okay, so now this a is also called as the activation function. Okay, this output a1 a2 a3 are often referred to as the activation functions. Okay, so this has to be remembered. Okay, so now how can we use vectorization for writing those examples? Okay, so now let us have a clear screen over here. So what we need to do is we need to represent w transpose x, and for representing w transpose x, so this is the input feature vector x, so we can write w transpose, and instead of writing x, I can write the input feature that vector x that I have written in the previous example. So this is my input feature vector x. I'll write this input feature vector x over here as x1 x2 that goes on till xm. Okay, so this is the way I can write a vectorized form of this equation here, or a part of this equation here. And what this w transpose would be, this would be a row vector. Okay, this row vector would be multiplied with this input feature vector x, and it would produce an output for w transpose x. Okay, so I hope this would have been understood to you. Okay, so now one thing has to be mentioned clearly is that this w transpose is the row vector. Okay, so what I can write here is that I need to represent this equation z equals to w transpose x plus b. Okay, so how I can write this equation? So basically this z would also be a kind of a row vector, so this could be represented as z1 z2 z3 that goes on till zm, because we have m number of training examples. Okay, and so what would be the dimensions of this output vector or row vector z? It would be 1 cross m vector, because this would contain a single row, and since we have m number of training examples, so this would have z1 z2 z3 till zm, so m number of columns. So this would be a 1 cross m dimension row vector. Okay, and that would be equal to w transpose x that we have already studied here. So this would be w transpose capital X plus. Now we need to write b. So while adding b, while you will write b in Python, you would directly write b. Okay, but in mathematical notation, when it is converted, this would be like b that goes on till b when it has completed over all the m training examples. Okay, so here the base vector b would also be the dimension of 1 cross m. So there would be basically m number of b's over here, because whatever would be the dimension of this output vector, the same would be the dimension of b. Okay, because b is ultimately added to w transpose x. Okay, so you need to have a sufficient number of b's also. Okay, so what if this b is added to this w transpose x, then we would get a vector somewhat as w transpose x1 plus b w transpose x2 plus b, that goes up to w transpose xm plus b. Okay, and this would be ultimately allocated to z1 z2, that goes up to zm. Also we can write this output feature vector z as capital Z. Okay, so this is the notation, and these are the small z, and this is the capital Z. Okay, so I hope this much is clear to you. Now how we can write in vectorized form whatever we have written over to here in the vector form, as z equal to np, and we would use the dot function over to here. We'll write w transpose comma x. Okay, so now this would be the vectorized implementation of our code. Okay, so this is the output z that we have written in the previous slide as z1 z2 z3. So we have got the values of z1 z2 and z3 till now. Now what I need to do is I need to find this activation function, that is a1 a2 a3, that would be equal to sigmoid of z1 sigmoid of z2 and sigmoid of z3. So what I can do here, I can again do vectorization here. Okay, and suppose that I represent this activation function as capital A, and this capital A would be equal to a1 a2 a3, and that goes on till am, because we have m number of training example, and also z goes from z1 z2 z3 to zm. So definitely we have to go from a1 a2 a3 till am, and that would be equal to sigmoid of z. Here this is the capital Z that I am writing here. So basically what you need to do here is you are allocating the value of while applying the sigmoid to all the values in the input feature output vector as z, and you are allocating the result of this over to this vector, and that is ultimately denoted as capital A. Okay, so this is the vectorized operation that we are performing here. Also what we need to do is we need to have some mathematical implementation of this function sigmoid, and we are going to do this in the next video lecture, as how we can represent this function sigmoid so that it can be applied in a vectorized form and can be implemented over here, so that our calculations and computations become very much easy. Okay, so now you can see that these are quite mysterious operations that are being performed over to here, because you can see that whenever you will write code in Python, you would not write this vector as b b b b and that goes on till m times. You'll simply write b over to there, and it will, what it will do, it would split in the form of m times of b. Okay, so this is a very mysterious operation that is performing by itself in the backend of the Python code. And what we often refer to this operation is, this term is known as broadcasting. Okay, this is basically known as broadcasting in Python, and this is a very useful concept. And if you want to know a bit more about this concept, then you can search on Wikipedia or any other programming site which you generally refer to. Okay, so this is a very important concept while studying for programming in neural networks and deep learning. So I hope this much would have been understood over to you. So in the next video lecture, what we are going to do, till now we have applied a forward propagation step in this computation graph of finding the vectorized logistic regression. Now in the next video lecture, what we are going to do is we are going to do the backward propagation, and we are going to find the gradient or the derivative. Okay, so this much over to you in this video lecture. I hope this video lecture would have been very much informative to you. If your friends are working in this field of neural networks and deep learning, then don't forget to share these video lectures to them also. I'll keep on sharing very good content and interesting examples over to you so that you could understand these lectures in a much easier way. Thank you for watching my video lectures. Subscribe to my channel, like my videos, and share to them on various social media platform also. Thank you so much.